Welcome to this tutorial. This is a follow-up on a previous tutorial where we modeled and analyzed a simple curved plate girder bridge. In this tutorial, we're going to go one step further and run an eigenvalue buckling analysis. This is why this box is checked here. So we don't need to go through the modeling process again. Feel free to go to a previous tutorial for that. Let's instead go to this form, the buckling analysis form, where we enter a 1 to say that we want to run an eigenvalue buckling analysis for this stage. And we've also clicked on the advanced button here to say that, hey, we want to narrow the search interval for the eigenvalues to between 0 and 3. And subspace dimension, which is kind of the number of eigenvalues that you expect at most, we will say it's equal to 10. Okay, it needs to be at least the number of eigenvalues within this interval. The reason why I'm specifying a search interval here is that if I don't, in this particular case, I will run into a lot of local buckling modes, and this will make the work for the eigensolver quite difficult. So here I'm just interested in the first few eigenvalues, so I'm just going to go to 0 and 3. Now let's hit next, and let's run the analysis. This form, as always, you can check the number of nodes, number of elements. Here we've got about 40,000 degrees of freedom. Feast here is the name of the eigensolver. It's now part of the Intel math libraries. So the analysis is run. Let's change the views. Let's make the loads smaller. These loads are modeling the weight of the wet concrete on top of the superstructure, as if the whole concrete deck was poured at once. So what's the stability of this bridge? And of course, it's a bit tricky because it's a curved bridge, so it won't have a behavior which is the one we would expect for straight girders, where almost suddenly we have a loss of stiffness. In this case, for curved bridges, the bridge deforms, and you would already see large displacements such as here, like about 5 inches, to say, hey, whether you've got a problem. Okay, so but we're still running a buckling analysis for the sake of seeing what's Embrace 3D can give you in terms of buckled shapes. So here it is. Let's zoom out a little bit here. Let's move the model a little bit. And we see here, let's turn off the axis. We have the first mode is an LTB mode, lateral-torsional buckling, between these brace points, between cross frame 3 and 4 on the third girder, and the eigenvalue is equal to 2.1. Let's scale this up a bit, and we can click on this button to see how it moves. That's the first buckling mode. The second buckling mode is a global lateral buckling mode. Okay, it's a bit higher at 2.9. So yeah, these are not super large eigenvalues, but we can see it's kind of expected here from this analysis, from the linear elastic analysis. The displacement's already pretty large. Okay. There is actually a third type of buckling mode that you can expect. It's the local buckling mode, the local web buckling mode, or local flange buckling mode. We haven't seen that here. That's because we specified a search interval that was small enough. But you may run into these type of modes, and that's something to remember when you run eigenvalue buckling analysis in Embrace 3D. So I hope this is useful. Please stay tuned for further tutorials.